13, it says problem solving with integration. Before we actually go on to doing that, and we've now reached the point where we've done all of the rules of integration that you need. Today's lesson is going to be doing a lesson which sometimes uses some of these rules in a more challenging way. It's a lesson of problem solving. It's a lesson of all demanding questions, I suppose. So can I quickly go through? These are the results for integration that we are going to need to use at some point today. If I can talk about these a second, they are all summarized all in one place on page 2. So first of all, on the left-hand side of this column, we've got the basic results of integration. X to the n, increase the power by 1, divide by the new power. E to the x integrates to give e to the x. Ln 1 and x becomes ln x. A to the x becomes a to the x over ln a. Sine becomes minus cos. Cos becomes minus sine. That in the first lesson. Then the second lesson, we did versions of all these rules where x is replaced by a linear function. So for example, ax plus b to the n, increase the power by 1, divide by the new power times the differential of the bracket, and so on and so forth. And we did a bit of trig integration in lesson 3. And then there's these results in the next table, which can basically be deduced from the formula booklet. And then finally, we did some work in the last lesson on use of trig identities to integrate more complicated trig functions. Now, the idea of today's lesson is this. There are 7 questions. The idea is you have a go at each question, and then we'll check the answer to it. So what I'm going to encourage you to do is question 1, go away, pause the video, and go away. Please stay there. Pause the video, have a go at the question, and then I'll go through an answer with it. And then similarly, question 2, pause the video, have a go at the question, do what you can do. Some of the questions are tricky. Some of the questions are not straightforward. Okay, so question 1 we'll talk about first of all. It says, by solving an equation, show that the curves y equals e to the 2x and y is 8e to the minus x intersect at x is ln 2. So that's the x coordinate of the intersection of these two graphs. And then hence show that the shaded area shown on this graph is 5 over 2. Pause the video, have a go, then check your answers. Okay, folks, so I'm going to do the first bit of this. So to find their point of intersection, you'll need to make the two equations equal to each other. So e to the 2x is 8e to the minus x. Now there is more than one way to solve this equation to get x is ln of 2. Here is a sensible approach. Other ways do work though. So 8 to the x, 2 to the x is 8e to the x. Going to ln both sides to get rid of the e. So you get 2x is ln of 8e to the minus x. You cannot on the right hand side cancel ln and e out because there's the 8 in between. But you can use laws of logs to write the right hand side as ln 8 plus ln of e to the x. ln 8 is 3 ln 2. And then ln of e to the minus x is just minus x. That then can be rearranged to give 3x is 3 ln 2, so x is ln 2. So that means we know that the x coordinate where they intersect is here. This is the shaded area we've got to work out. We are going to do this by finding the area under this graph, which is the top graph for the function, ae to the minus x, and then subtracting the area underneath that. So the area under 8e to the minus x is the integral. Both areas start at x is 0 of 8e to the minus x. E to the power of a linear function, you do 8 divided by minus 1, so that's minus 8e to the minus x. Sub in x is ln 2, sub in x is 0, and subtract. Now, because it is a show that question, a little bit of laws of logs is needed to simplify this first term here. So 8e to the minus ln 2 is 8e to the ln of a half, taking the minus 1 inside as a power, and therefore the first term is minus 8 times a half. Second term is 8, so that area is equal to 4. Then the area under the second graph is the integral from 0 to ln 2 of e to the 2x, which integrates to give a half e to the 2x. Sub in x is ln 2, sub in x is 0, and subtract. The first term, using laws of logs, becomes a half e to the ln 4, which is a half times 4. The second term becomes a half e to the 0, which is just a half. So that is a 3/2. Therefore, the shaded area is the difference between them. 4 take away 3/2 is 5/2. And we are done. Pause the video if you need more time with that. Here is question 2. So question 2 says the curve y equals root 4x minus 3 and the normal at the 0.75 are shown. I need to find the exact shaded area, fully justifying my answer. So again, pause the video, have a good go at it, have a think about it, and then use the solution to check your answers. Okay, here is my thoughts on this one. So first of all, we are going to at some point have to write root 4x minus 3 as 4x minus 3 to the power of a half. In order to work out, sorry folks, in order to work out the shaded area, I'm actually going to split it into two. Part of the area is the area under the curve, and then part of the area is the area under the normal. We're going to have to work out those two areas separately and then add them together. So area 1 is the following, and you can check that this curve, the area starts at 3/4, because if you make that equal to 0, you get 4x minus 3 is 0, so x is 3/4. So area 1 is the integral from 3/4 to 7 of 4x minus 3 to the half dx. Integration, increase the power by 1, you get 4x minus 3 to the power of 3/2. The new power times the differential of the bracket is 3/2 times 4, which is 6, so it's 1/6, between 7 and 3/4. And if you then sub in x is 7 and sub in x is 3/4, you can use your calculator, you'll get 25/6, take away 0, which is 25/6. So I've now worked out area 1. The remaining part of this is actually, I suppose, a triangle. So we can do this by finding a half base times height. And the height we already know, it's the y coordinates of the point on the curve, so that's 5. The tricky bit is to work out the base. To find the base, you're going to have to find this point Q, because the base is from the distance from 7 to Q. And to get Q, you've got to find where the normal crosses the x-axis. And to do that, you need to find the equation of the normal. And to do that, you need to do some differentiation. So this is a question with a bit of differentiation and integration put in. So if you differentiate to get dy by dx, it's the power, which is a half, times the differential of the bracket, which is 4. So that gives me 2 times the bracket with the power reduced by 1. 4x minus 3 to the minus a half. That's what it differentiates to give. Sub in x is 7, because at the point on the curve x is 7, and this will give you 2/5. So 2/5 is the gradient of the curve, which is the gradient of the tangent. Therefore, the gradient of the normal is minus 5/2, because it's the negative reciprocal. So consequently, the equation of the normal is y minus y1 is mx minus x1, y minus 5 is minus 5/2, brackets x minus 7. Now, at this point Q, the y coordinate is 0. So what you don't have to rearrange the equation of the normal. You can just plug in y is 0 into that, and you get minus 5 is minus 5/2, a bracket x minus 7. Divide through by minus 5/2, you'll get 2 is x minus 7, which means x is 9. And now we're okay, because this point has an x coordinate of 9. So therefore, the base of the triangle is 2 units. So the area of triangle 2 is a half times 2 times 5, which is 5. You can get that, by the way, if you want, by integrating the equation of the normal. You should get the same answer. Therefore, the total area is 25/6, add on 5, which is 55/6. If necessary, pause the video, write that up, and then we'll have a go at the next one. Here is question 3. Question 3, it says the following: the curve y equals 1 over 2x plus 1, take away a third, intersects the x-axis at the point 1, 0. So that means that's the point 1, 0 there. I've got to show that the area bounded by the curve and the x-axis and the y-axis and the line at x is 2. So this is this total area here is given by a half ln 9 over 5. And it asks you to justify your answer. Please pause the video. Please have a go at it. Then I'll go through the answer. So, lovely students, added that information onto it here. In order to work out the area, because part of it is above and part of it's below, integration, the bit below, will come out as negative. So I'm going to have to work out these two areas separately. I'm going to have to get rid of the negative sign for area 2, and then we'll add them together afterwards. So first of all, here's area 1. It's the integral from 0 to 1 of 1 over 2x minus 1. Sorry, 1 over 2x plus 1. There's a slight typo there. Take away a third, which if you do your integration is a half ln mod 2x plus 1 minus 1. Take away a third just integrates to give a third x. If you then sub in x is 1, sub in x is 0 and subtract, this is what you'll get for doing that. And then a little bit of simplification. So this is going to give me, for the first term, half ln mod 2x plus 1 is a half ln 3. Take away a third. The second bracket, well, that's ln of 1, which is 0, and that's 0. So the second bracket is 0. So the exact area of 1 is a half ln 3 minus a third. I now need to work out the exact area of part 2. So to do the area of part 2, it's the same integral, but this time from 1 to 2, but I know that my final answer is going to come out to be negative. So integral, same as before, half ln mod 2x plus 1 minus a third x. This time, sub in x is equal to 2, sub in x is equal to 1, and subtract. And this will simplify to give a half ln 5 minus 2/3 minus a half ln 2 plus a third. So that's what that integral gives you. Now, if you were to type that into your calculator, it will give you a negative value because this is below the x-axis. The actual area of this is got by timesing that by minus 1 to make it positive. So therefore it's minus a half ln 5 plus a half ln 3 plus 1/3. So therefore, if I add that area and that area together, now I've changed the sign, I should get the correct answer. So the total area is half ln 3 minus a third minus a half ln 5 plus a half ln 3 plus a third. Now the thirds will cancel and you'll get that expression there. To give it in the required form, if you take out a half as a common factor, what you have is essentially ln 3 add ln 3 take away ln 5, which is ln of 3 times 3 over 5. So consequently, that's a half ln of 9/5 as required. Pause the video if you need. Write up what you've got. Have a good think about it. Let's go on to question 4. So question 4 is actually a trig integral one, which is a little bit easier than the three previous questions. Express cos 2x in terms of sine x, hence find the integral of sine squared x. Pause the video, have a go at it, then I will go through the answer to question 4. Okay, folks, so this is just meant to be written down from knowing your trig identities. The formula that links cos 2x and sine x is cos 2x is 1 minus 2 sine squared x. Hence find the integral of sine squared x. Well, if you rearrange that to get sine squared x in terms of cos 2x, you will get sine squared x is a half minus a half cos 2x. The integral of a half gives you a half x. And then the integral of cos 2x is a half sine 2x. So it's a half x minus a quarter sine 2x plus c. Okay. Question 5. So question 5 says, show that the derivative of sec x can be written as sec x tan x. That's part A. So that's a differentiation question. Derivative means find dy by dx. And then part B asked you to hence, well, it doesn't say hence, but trust me, it is related, find a particular integral. So I'll do part A first of all, and I'll try to explain part B. So this is the differentiation question. So I'm going to write y as sec x, and I know, because the third letter is C, sec is 1 over cos. Now, to differentiate something divided by something, you can use the quotient rule. This is differentiation. You can, if you want, write it as cos x in brackets to the -1 and use the chain rule. It works in a similar way. So u is 1, which differentiates to give 0. V is cos, which differentiates to give minus sine. So this is what the quotient rule gives you for this. It's cos x times 0, take away 1 times minus sine x divided by cos squared x, which gives you sine x on the top, because 0 times cos is 0 over cos squared. Now, looking at the answer, I can split this into 1 over cos times sine over cos, and 1 over cos is sec, sine over cos is tan. Now, part B is a very, very, very unpleasant looking integral. The integral of tan over 1 plus root cos 2x. And I think if you weren't given part A, this question would be completely impossible. Even given part A, it is not obvious what to do. My hope and pray is the following. I know that sec differentiates to give sec tan. So therefore, if you integrate sec times tan, you must get sec. Hopefully, I can rewrite this formula to be integrated in a way that is either exactly sec times tan or something related to sec times tan, and then I can integrate it. Here is what happens. So leave the tan x by itself on the top. I want to try to write this as sec times tan. I want a tan in the answer. On the bottom, replace cos 2x with 2 cos squared x minus 1. So you get tan over the square root of 1 plus 2 cos squared x minus 1. Now the plus and minus 1's cancel, so you get the integral of tan x over root of 2 cos squared x. And that's okay, because I can just square root the first, and that's root 2, and square root the second, and that's just cos. So it's the integral of tan over root 2 cos. But wait a minute, 1 over cos is sec. So dividing by cos is the same as multiplying by sec. So this is the integral of 1 over root 2 times 1 over cos, which is sec, times tan x. We know that the integral of sec times tan is sec. So the integral of this is therefore 1 over root 2 sec x plus c. Pause that if necessary. Then I'll have a go at question 6. So question 6 is the part A is a trig identity question and part B has got some integration in it. So part A says by writing sine 3x as sine of x plus x, show that sine 3x is 3 sine minus 4 sine cubed x. Part B asks me to hence integrate sine cubed x. Pause the video, have a go at it, then I'll go through the answers. Okay, so here's the first part of this. This is a trig identity problem. So sine 3x is sine of x plus 2x. That's what we're asked to do. Now this has the form sine a plus b. So if you use your sine a plus b identity, which says it's on the formula sheet, sine a plus b is sine a cos b add cos a sine b, this becomes sine x cos 2x plus cos x sine 2x. You get a mark for doing that. Then I've got double angle formulae that I can replace cos 2x and sine 2x with. Now I'm going to choose the formula for cos 2x, which has sines in. So the first term becomes sine x times 1 minus 2 sine squared x in a bracket. I'm going to replace sine 2x with 2 sine x cos x. So the second term becomes cos x times 2 sine x cos x in a bracket. If you expand the brackets, in the first case, you get sine minus 2 sine cubed. In the second case, you're just multiplying things together, you get 2 sine x cos squared, and we are nearly there. The main thing I need to do is to get rid of that cos squared x. So I'm now going to replace that with 1 minus sine squared x in a bracket to give sine minus 2 sine cubed plus 2 sine times 1 minus sine squared in a bracket. Expand that bracket and you get sine x minus 2 sine cubed plus 2 sine x minus 2 sine cubed, which is indeed 3 sine x minus 4 sine cubed x. Now, let's have a think about part B. Part B is actually easier than part A. Hence means you have to use the original part of the thing. You have to use that identity. I want to integrate sine cubed x, and I notice that sine cubed x is part of the formula on the right-hand side. So what I'm going to do is rearrange this identity to get sine cubed x by itself and then integrate the thing on the other side instead. And actually, this turns out okay. So if you get the 4 sine cubed x term by itself, you'll get 4 sine cubed x. Sorry, that's my terrible handwriting. I must have made a mistake on this. Is 3 sine x minus sine 3x. That's taken the 4 sine cubed across and the sine 3x back, and then divided by 4, you'll get sine cubed x is 3/4 sine x minus 1/4 sine 3x. And these are two terms that we can just write down the integral for. So if you integrate 3/4 sine 3x sine x, you will get, well, sine becomes minus cos minus 3/4 cos x. If you integrate 1/4 sine 3x, or sine 3x will integrate to give minus 1/3 cos 3x, times it by minus 1/4, and you'll get plus 12 cos 3x plus c. Pause that if you need, write it up, and then we have one more to go. So question 7 asks you to do the following. Show that the area of the region bounded by the curve y equals tan x and the horizontal line which intersects the curves at x is plus or minus pi over 4. These are obviously angles in radians. I've got to show that the exact shaded area here is given by pi minus 2. Pause the video, have a go at it, then I'll go through the answer. Okay, students, here is my model solution to this. I am first of all going to work out the area underneath the curve. That's going to give me this area here. I'm then going to subtract that from the area of this rectangle here to get the shaded area that I want. So I'm going to do the area under the curve first of all. I'm doing this bit. Now, guys, you could do it by symmetry by just going from 0 to pi over 4, but I'm going to do it in one go. So the area under the curve is the integral from minus pi over 4 to pi over 4 of tan squared x. To integrate tan squared, write it as sec squared minus 1. Sec squared integrates to give tan, and 1 integrates to give x. Then sub in x is pi over 4, sub in x is minus pi over 4, and subtract, and you will get this line here. Tan pi over 4, take away pi over 4, take away tan of minus pi over 4, take away minus pi over 4. There's a bracket missing there. If you simplify, your calculator will happily tell you that tan pi over 4 is 1, and that tan of minus pi over 4 is minus 1. You get 1 minus pi over 4 plus 1 minus pi over 4. If you collect like terms, that's 2 take away pi over 2. Now, to get the shaded area, I've got to subtract it from this green triangle. The base of the triangle goes from minus pi over 4 to pi over 4. So that's 2 lots of pi over 4, that's pi over 2. The height is given by the y value when x is either pi over 4 or minus pi over 4. It's symmetrical, so I can choose either point. So I'm just going to choose pi over 4 because it's easier. So the height of the triangle is when x is pi over 4, y is tan squared of pi over 4, which means tan of pi over 4 in brackets squared, which your calculator will happily tell you is 1 squared and therefore 1. So because the base of the rectangle has got width pi over 2, the area of the rectangle is pi over 2 times 1, which is just pi over 2. So consequently, the shaded area is the area of the rectangle, which is pi over 2, take away the area under the curve, which we worked out earlier, which is 2 minus pi over 2 in a bracket. If you remove that bracket, you'll get pi over 2 plus pi over 2, which is pi, take away 2, and we are done. Now, lovely students, that was deliberately supposed to be some questions which are approaching as difficult as integration gets. Can I explain to you for a second the expectation with regards to the exercise from this lesson? So consolidation exercise 4 has two sections, section A and section B. You should either do section A or section B, or if you're really keen and want some more practice, both is obviously fine. You don't have to do both of them. Section A is more routine questions, but they're still not an absolute doddle. Section A has these questions here. Turn over the next page and they carry on a little bit, going up to question 6. Question B has more challenging exam standard questions, questions along the line in terms of their difficulty of the rest of the questions we've done here. So either do, if you feel confident on integration, you do section B. If you feel that X lesson was quite tough, it's fair enough, it's not straightforward, it's fine for you to do section A. Okay, folks, we are done.